So first of all, thank you very much for coming for my talk. Today I'm going to talk about the architecture of Kotlin Multiplatform projects, and in particular, what can we do for better scalability and maintainability. So I've been looking around the community open source projects for different architectures. They are mostly samples. Like everyone likes writing samples. There are quite a few production open source projects, but what works well in a sample project most likely will not be a good fit for a production project at scale. Anyway, there seems to be a noticeable pattern that many projects use. So they tend to create one single shared Gradle module. Usually it's called just shared, which is created by default when you click File, New Project in the IDE. There are a number of view modules in that shared module, typically one view module per each screen. And then there are app modules, one for Android, one for iOS, and so on. And each app module contains a platform-specific UI and navigation. This works pretty well in sample projects. Shared and multi-platform specific things are separated. It's easy to browse through files in the folders, etc. But there are also some problems with this approach. Let's consider some use cases. What if we need to add a new screen, for example? We have to not only change the shared module, but also update both app modules. Need to remove a screen, again, also touch the app modules. Need to change the communication between some screens, yes, update all of app modules. And the same issue is changing the navigation logic. And another concern is that all modules grow linearly. Almost every time we add a new code to shared module, we have to add counterparts to the app modules. And unfortunately, this affects the maintainability of the project. Just imagine a module with hundreds or thousands of view models, their dependencies, and all that stuff. Another side effect is the increase of chances of merger conflicts with other colleagues, especially if the team is big. And it's also not good for build times. We can partially improve the situation by splitting the shared module by a number of feature modules, but still having monolith application modules is not good at scale. So how can we do better? Let's consider an example. The Twitter app, the most of us should have handy on our devices. As a disclaimer, I don't work for Twitter. I just like the social network, and its mobile application looks pretty good as an example of a complex project. The first screen the user sees is the landing screen. This is the step where the user decides either to log in with an existing account or to create a new one. If the user selects the login option, there are two more screens to enter an email address and a password. The sign-up flow contains screens to enter some personal information and to customize things like personalized ads and etc. Once the sign-in or sign-up flow is finished, the user is taken to the home screen. This is the default screen of the app. It's shown by default when the app is opened and the user is already signed in. From the home screen, the user can go to different places like profile, settings, or the tweet screen. And the home screen itself is not just a single screen. The user can use the bottom tab bar to switch between other screens like search or spaces. And of course, there are more screens in the app, and there must be a lot of code. So how can we organize all that? How can we allow different teams to work productively on the same code base? And how can we make sure that the code is testable and maintainable? I'm going to present an interesting approach, I call it thinking in scopes. Thinking in scopes. Let's again use the Twitter app as an example and decompose the app by a number of scopes. Again, it's just an example, nothing related to the real app. The topmost scope is the root scope. This is the scope that is created at the very beginning of the app's lifecycle. It holds everything that works in the app. All the logic, repositories, data sources, everything is inside this root scope. And everything that should exist only while the user is not signed in can belong to a sign out scope. This scope can contain additional, I would say, subscopes, sign in and sign up. And sign in scope hold the login flow, and the sign up scope hold the registration flow. The landing screen can live in its own scope, so the parent signed out one, the green one, controls the three children and switches between them when necessary. The sign-in scope contains screens of the login flow. Its responsibility is to switch between child screen or child scopes. And the same story with sign-up scope. It contains screen for the registration flow and navigates between them. Once the user is signed in, the root scope can destroy the sign-out scope, the green one, and create another one, sign-in scope, orange color. This scope exists while the user is signed in. On logout, the root scope can switch back to the sign-out scope. Here we have the main tab scope and other child screens like profile, settings, or tweet. The sign-in scope, orange, can switch between full screen ones. For instance, when the user clicks on a tweet, the signed-in scope can push tweet into the stack. And lastly, the main tab scope just contains the tab screens, home, search, spaces, etc. Every time user clicks on a tab in the bottom tab bar, the main tab scope just replaces the current screen with another one. So the structure that I have just described is actually a tree structure. Each parent node is only aware of its immediate children, and each such node has very limited responsibility, either to hold and manage the logic of a scope or to switch between child scopes. And yes, the tree structure is scalable. For instance, if you want to add a new module, like, for example, a new screen, we just add new module and attach to a parent. In most of the cases, we have to only touch one specific parent scope. And our new module is there. If you want to remove a screen, it's also easy to just delete the child module and update the parent. And the screen is gone. A module may become bloated and difficult to maintain. And in this case, it can be decomposed by a number of smaller submodules. Each with more limited responsibility, the parent module will just simply manage the children. And same if you want to change communication between child scopes, just update the parent module, change navigation logic, update the parent. In a tree structure, each module has limited and meaningful dependencies, so there are no good modules. And obviously, this reduces chances of merge conflicts in big teams. And yes, it's good for build speed, as more code can be compiled in parallel. So far, so good. So how can we implement that? Let's think about requirements. Every parent node should be able to manage scopes of its immediate children. This means that child scopes should never be longer than the parent. And next, it should be possible to easily switch children in a parent, which means we need navigation. Nodes should be lifecycle aware, so we can scope tasks inside a node. For instance, cancel a task on destroy or refresh data on resume. And last but not least, it should be possible to save state in a node. This is useful for handling configuration changes and process death on Android, but probably not only Android, because iOS have kind of same concerns. And there is a library exactly for that purpose. It's called Decompose. It helps to break up the code into meaningful lifecycle-aware components, organize it as trees. Each component has its own scope. And there are tools for switching subtrees, or in other words, navigation. So let me describe a few most important features of the library. First of all, it draws clear boundaries between UI and non-UI code. This gives the ability to plug almost any kind of user interface, like Jetpack Compose, Swift UI, or React. And also it makes components easy to test with just normal unit or integration tests and without instrumentation in most of the cases, which is fast and reliable. It also enables classic dependency injection and inversion of control. This is very useful in large projects when a component should be reused in different places. The navigation logic can be shared. Components are lifecycle aware. This makes it possible to scope background tasks and handle lifecycle events. And of course, it's multi-platform. The core of the library supports Android, all Apple targets, JVM, and JavaScript. There are also some additional features like convenient state preservation and instance retaining, also known as view models on Android, and back button handling. And there are also separate extension modules for Jetpack Compose and classic Android views. So here you can see some links to most interesting sample projects that showcase the library from different perspectives. The first one is the to-do app in multi-platform Compose repository. It's just a simple list details application with multiple feature modules and persistent storage. It also demonstrates unit and integration tests. And another one is a multi-purpose sample app showcasing different kinds of navigation. So let's start with a brief explanation of the most important entity of the library. What is component? So first of all, it's just a normal class. So any class can be a component. Components can encapsulate some logic, just like well-known view models. And they can also encapsulate and manage other child components. Every component has its own life cycle, automatically controlled by Decompose. The user interface is attached externally. Components do not depend on the UI. The UI depends on components. So let's walk through some simple examples. As I mentioned earlier, any class can be a component, even an empty one. Decompose doesn't require component classes to extend any base or abstract classes or to implement any interfaces. But most likely you will find useful to extract an interface. Some use cases could be to inject test implementations when testing parent components, for example, when you want to test navigation, or to provide separate implementations for Jetpack Compose or SwiftUI previews, but this is completely optional. If you need an access to lifecycle or back button handler, or if you need to preserve some state, or if you need navigation, then component context should be supplied via construction. Component context is the second important entity of the library. Each component has its own context. Decompose always provides dedicated context for every component. It's up to you if you want to inject it or not. Component context is just a simple interface with a few properties. It's not related to the Android context in any way. It provides access to the lifecycle by the corresponding property. There are also tools for state preservation, instance retaining, and back button handling. All this together makes it possible to integrate and scope child components with persistent navigation. As mentioned earlier, component context is a simple interface. So delegation can be used to bring the properties of the interface into this scope. The lifecycle is very similar to Android. Here you can see all possible transitions. So at the beginning, the lifecycle is initiated, then it goes to the created state where it can go either forward to started or back to destroyed, and from started it can go to resumed or back to created. Very similar to Android. And it's multi-platform in all targets. The lifecycle can be accessed by the corresponding property, so it's possible to subscribe for lifecycle callbacks, like on start, on resume, and so on. And it also makes it possible to scope background tasks. For instance, we can define a coroutine scope and cancel it on destroy, or we can dispose any disposables if NRX library, for example, is used. And now about child components. Creating and managing children with Decompose is easy and safe and can be done in different ways. The simplest way is to just create a child component directly during the initialization of the parent. These are so-called permanent components, so they live as long as the parent. So as I said earlier, Decompose provides child context for every component. In this case, the child context extension function creates a child context for you, and you can inject it via constructor to a child component. And we can also manually control the lifecycle of such child components. For this case, we can just use the lifecycle registry, like similar name as in Android, and manually call start or stop if you want. So, but managing children manually may be difficult, for example, when navigation is required. And Decompose provides handy tools for navigation. For instance, there is child stack for stack navigation. It's important to understand some key concepts of stack navigation. For example, here is the first one. Each component in the stack has a configuration class. You can think of it as a serializable holder of arguments. You have to define a configuration class for every child that can be in the stack. To initialize the stack, it's required to supply a child factory function. The function accepts two arguments, a child configuration and a context, and returns a new instance of the corresponding child component. This is a place where you can call the child constructors, and here you can safely supply all the required dependencies and arguments. Configurations are unique keys. They must properly implement equals and hashcode methods, or just be data classes. And configurations are persistent. Decompose automatically saves and restores the stack of configurations when needed. And every configuration class must implement the parseable interface, which is provided by Decompose and is available in common source set. The library also provides parcelize annotation, so make sure you have the Kotlin parcelize plugin applied if you're targeting Android, of course. And the last concept specifies how the navigation is performed. The navigation is just a function from the old configuration stack to a new one. The basic navigate method accepts the transformer function that changes the stack. So here's an example. We can define a couple of child components. They can accept any kind of dependencies, including callbacks. In this case, the main component accepts its own context, as well as the main coroutine context and a callback that's invoked when, for example, an item is clicked. The details component also accepts the main coroutine context and an ID of the item to be displayed. As you can see, we benefit from strict type safety. It's not possible to mess with types. The project will not compile otherwise. In the root component interface, we can specify all possible children as a sealed class or interface, and later this will allow us to exhaustively handle all children and also avoid any casting. In the root component implementation, we have to define a configuration class for every child component. In this case, we define two classes, main and details. We can also define persistent arguments, for example, item ID. Again, we have full compile time safety here. And now we can add factory methods for children. We create them by calling constructors and supplying all arguments. As usual, everything is compile time safe. And the same for details component. You can see the persistent arguments are taken from the child configuration. Non-persistent arguments can be created on demand or taken from the parent component. And now we can add main factory functions that exhaustively switch all child configurations and create the corresponding component. Now it's time to initialize the stack. First of all, we need to create stack navigation. It's like a simple relay of navigation events. So it's possible to subscribe to navigation events and send navigation events when we want to navigate. And lastly, we create the child stack by calling the corresponding extension function. And we supply the source, which is like our navigation. And we also can supply initial configuration or initial stack, which will be used if there is no previously saved state. We can also supply handleback button flag, which tells child stack to automatically handle back button presses. For example, it will pop the stack when the button is pressed. And the last argument is the child factory. We can simply pass a reference to the factory function we have already created. And now the child stack is initialized and the project compiles. Most likely it will just work. And now we can navigate. For example, we can push the details component when an item is selected. We can also pass arguments safely here. And don't forget that the navigation is just a simple transformer function from old stack to a new one. Because configurations are unique keys in the stack, we can transform the stack as we like. Decompose automatically activates new components and deactivates old ones. For instance, we can reverse the stack or just shuffle it if you want. And the child stack is not the only navigation model. So there is child stack, as I described it, just in child stack there is only one active child component at the top of the stack, and there is a back stack of inactive components. It works best for push-pop navigations, bottom navigations, and so on. Another navigation model is child overlay. There can be either one active component or none. It works best if you want to switch child components dynamically, present dialogues or bottom sheets. And of course, it's possible to create custom navigation models if something is not working well for you or you need something special. So there's pretty flexible APIs that allows almost any kind of navigation. But what about user interface? As I mentioned earlier, the user interface is plugged externally. Components do not depend on the user interface, but the user interface depends on components. So here is an example of how we can display the child stack. We should export the child stack state from the component and make it observable. One of the ways is to use value. It's a Swift-friendly way of exposing stateful observables provided by the library. But you can use coroutines flow or RX instead of value if you like. And after that, we should just override the property in the root implementation and return the child stack. And now how can we display this stack? For instance, Decompose provides the children function for Jetpack Compose that automatically displays only the active component. This is the place where we exhaustively switch the children. And it's also possible to specify different kind of animations. So there are some animations available out of the box, or you can define your own. For example, this is a sample crossfade animation. Here is the slide animation. And we can also combine animations using the plus operator. Here's an example of combined crossfade and scale animation. We can also specify different animations for different screens. And as I mentioned earlier, we can plug any kind of UI, like Swift UI for iOS, Compose for desktop, or React for web. And we can do single multi-pane layouts, or even dynamic layouts. And I think that's all. Here's a link to the repository where you can also find documentation and samples, and also my Twitter handle in case you would like to follow me. And if there are any questions, I am happy to answer.